Hi twin, this is the alternating series, so basically you just use this test when your series is like negative, because like all the other tests you use when it's like only positive. So this one, if it's negative, you use alternating series. Okay. This is just like saying if it's negative, it can come in the form of like this right here, or over here. It can also look like that for like the negative. Like when you plug in whatever n is, it's going to be like change the sign from negative to positive, is what that is saying. So basically the alternating series test is when if all three of these conditions down here are like satisfied, then that means the series is convergent. So the first condition is if b sub n, like okay here, yeah. So if b sub n here is greater than or equal than 0, so it's all like positive, all real numbers for n. If you check that one off, check if b sub n is decreasing. If that's true, check that off. And then if the limit of b sub n equals 0. So if all of these are true, then the series will be convergent. And if one of these fails, then that means the series is either convergent or divergent, and you just need to use a different test to check. In this case, if here, let me erase this. If the second one fails here, b sub n is decreasing, that just means use different test. Wow, my handwriting's, wow, that's really ugly, man. I'm on a mouse, man. You can't judge me. Oof, use diff test, okay? To check whether it's convergent or divergent. But if the second one fails here, the third one fails, then that means the series is divergent by the test for divergence. So wait, I'll write it out. If a limit, so like on the test or quiz or whatever it is, and the third one here fails, you can just write this as your answer, or like as your explanation, but like neater. And then whatever b sub n is, diverge by test for divergence. So yeah. So basically that's that. And I'll do some examples. Okay. So okay, this is our thing. So I usually rewrite it out, so it's easier to look at. So we have the sign here. So the sign is plus 1, and then if you write it like this, because you can see clearly that this is a sign, and this is your b sub n. Right. So now we do the now we check for the conditions. Check. Ooh. So first one, it's is b sub n positive for all real numbers? It's 1, yeah, right? Because n equals 1, so any number you plug in will be positive. So yeah. Second one, b sub n is decreasing. Sorry. You see the b sub n is 1 over n, so whatever you plug in, it will always be decreasing. So check. Wow, that's an ugly check. Third one, if the limit of b sub n equals 0, so we can work that out. So this, well, it's 1 over n, so it would just be like this, and then 1 over n, and we know that any constant with infinity on the bottom would equal 0. So yep, this is a check right here, which means a series, whatever the series is, yeah, I'll write it out. N plus 1 over n converge by the AST, or alternating series test. It's whatever. It's just like saving time. Okay, next, I'll let you look at it. Let you look at my beautiful handwriting twin. Okay, and then I'll go to the next question. Okay, so now determine if this series converges or diverges. Okay, so we can see here that this is the sign. This one over here is b sub n, right? So here I can. So now we do the check thing. So 1 is b sub n greater than or equal to 0. Wow, that's beautiful. Okay. So that's yeah, right? Because remember so like when your b sub n looks like this with like a -1 or +1, you use the Elon Musk metaphor, which is like if Elon Musk loses $1, he's not gonna notice, and then if Elon Musk found $1, he wouldn't notice anyways. So basically using that, we can rewrite this as b sub n equals 1 over n. Okay, and then when you're doing when you check for the first one, well, it's yeah, all right, and then because we know like this graph, wow, I'm really good at explaining this. Looks like that. Wow, no, it doesn't. It looks like this. No, it looks like this. Yeah, there we go. And then so that means that when it's 1 over n, it's gonna look something like this. Perfect. Except right, and it's like yeah, close enough. But basically, it's never gonna go below 0. So the first one, check. Okay, second one is b sub n decreasing. Well, we look at the graph. Wow, it's decreasing. Well, we look at the graph, and yeah, it's decreasing. So that's a check. And then we check the third one. Limit b sub n equal to 0. So our thing is our b sub n equals wow, sorry, twin, e1 over n minus 1. Okay, so well, let me write this, don't forget this. So we got, so 1 over, if we substitute the n with infinity, that's going to be e over 0 minus 1, and then e, anything to the power 0 is 1, so yep, that equals 0. Check. So we know, so we can write the series. Wow. Sorry, twin. Don't touch me, twin. Okay. Converges by the alternate series test. Boom, perfect. Okay, I'll let you look at it, and then excellent. Let's see. So for this one, again, we can see that this will be the sign, and then the rest will be our piece of it, which is kind of like what we just did before, like the same graph, basically. So we do the check. Good. So we check a piece of n is greater than, wow, 0, and then based on the graph, we know this is true. Second one, if piece of n decreasing, we put degree. Yep, that's also true. So now the last one, limit n approaching infinity, piece of n, and our piece of n in this case is e to the 1 over n, right? So then we substitute the n, we know it's going to be like, oopsies, it's going to be e to the 0, and whatever is to the power 0 is 1, right? So now we know that this one's false, right? Or like not true. And you know, remember what I said in the beginning, if the third one fails, then that means it the series diverges by the test for divergence. So in this one, we could just write the test, or the series, nope, I don't know when I changed colors, but I changed colors at some point. Okay, diverge by test for divergence. Yep, and then that should be enough. Here's 2 points. Okay. All right. There's, for the alternary series, there's like 3 different, like, I guess like subtests or whatever. So the first one is like just normal. You're doing the test. So the first one is just a normal one, and the second one is like testing if it's absolutely or conditionally convergent. So it's conditionally, wow, convergent. And then the third one is the alternating series estimation theorem, and I'll explain that later. So here. So sometimes like the test, you see in this equation or example, it's gonna ask you to find whether or not the series is convergent or divergent, and then it's gonna ask you, does it converge conditionally or absolutely? So basically, what that means is you do it the first time, right? Using the alternating series test, and then you do it again, but you take the absolute value to see it. So you use the test on just the normal a sub n, right? And then you do the test again on the absolute value of a sub n, right? And then wow, I did not give myself any room. Let me rewrite this. Let me put it over here. Oopsies. Okay. So basically, if, say, it converges... Oh, I did not do this in a... Wait. Sorry, twin, don't look. Twin, close your eyes. Okay. Not open it right now, twin. So ignore everything I just said, okay? Ignore my fumbling, twin. So this is the thing of a sub n, and then the absolute value of a sub n, right? Okay, so if a sub n converges, well, in this case, it's going to have to converge if you want to ask if it converges conditionally or absolutely. So if it converges normally, and it also converges when you take the absolute value of the thing, that's, here, I'll write it in a different color. That means that it absolutely converges. So absolutely is convergent, this one right here. And if it, converges normally, but diverges when you take the absolute value of it, then that's conditionally convergent. Right, this one right here, right? So yeah, so I'll do an example. So you see in this case, this right here is our sign, because when you take, when you plug in the numbers, it's gonna change from everyone's or whatever. So that's gonna change the sign. So we can write, if you rewrite it, so we have 6 cosine, and then so we know that this is the sign. And wow, I didn't even notice how ugly that n was. Okay, and this is our piece of n. You don't have to write this out, but it just like helps me to like separate them, I guess. Okay, so now we do the alternating test, right? So we check it. The first one, piece of n is positive for all the numbers, right? And the graph again, right? So based on the graph, we know, yep, that's all positive numbers. And then, oopsies, I forgot to check over here. Ignore that time. Okay. And then our next one is if piece of n is decreasing. Again, the graph, so yes, we know that's true. Make sure you have memorized your graphs, twin, okay? And then the third one, the limit of p sub n in this case is if this is approaching 0. So let's see, right? Take the limit of approaching infinity, right? And then the logarithm approaching infinity is infinity, so then that's 1 over infinity, and then that's going to equal 0. So yep, ooh, wow. So it's S0, okay. So now that's all true. So now we know that, yes, the series converges, right? So now we're going to do the second part of the example, which if it converges, does it converge conditionally or absolutely? So this is, I'll write this first part, oh, and this is the second part, okay? So remember when we do this, we take the absolute value of a sub n, and the a sub n in this case is like the whole thing, okay? So doo-doo-doo. Okay, and well, when you look at this, right, the cosine of pi n, you know that's just -1, right? And so since we know that cosine pi times n is -1, when you take the absolute value of that, that's just 1. So we can rewrite this so it looks a little like prettier like that, okay? So then when you do the test again, and also the logarithm of n is positive always, so we can rewrite it like this. Oh, well, I just rewrote it like that. Anyways. And then in this case, like you're thinking, okay, so what now? Because we can't use the alternating test, which is what we did in part 1, right? So we have to use a different test because it's not alternating. And in this case, I'll give you a second to think. I'll do like Dora the Explorer. What test should we use, twin? Okay, have you thought about it? The answer is we use the generalized p-test. I guess a little refresher. I'll do a little refresher right here. The generalized. Jesus, my handwriting, man. Because it's basically when you have the logarithm stuff. Let's see. So like an example would be if you had like whatever n is, like say n is 2, and then we have log of whatever, just say like that, right? In this first one, you just do normal p-test, so you see whatever the p is, and in this case, p is equal to 2, which we know using the p-test is greater than 1, so this converges, right? Another example, but like say if the equation was n and then say it was like, I don't know, like 3 or something, right? And this, when it looks like this, and p is equal to 1, we then look at whatever the exponent is for the logarithm. So in this case, well, I guess I can't call it p, so I'll call it q is equal to 3. And then the rules are for this test is if q is greater than 1, then it converges. And then if q is less than or equal to 1, then it diverges. But also, if say p for it, since p is the first one, right, the n right here, and the invisible one, if p is greater than 1, it converges like normal. If p is less than 1, it diverges. But if p is equal to 1, then we look at whatever q is, and then we decide from there. So that's our little like review. So let me just go back up here. So here, I'll just rewrite here. So since there's going to be an invisible n right here, right? So we can look at this and use the generalized p-test. So p equals 0, which in this case I could just write it here, which we know it diverges, right? Because p equals to 0, and we know so yeah. So whenever p is less than 1, it diverges. If it's greater than 1, converges. If it's equal to 1, you look at whatever q is. So you write diverges by the generalized p-test as your explanation, and then you have an add like p equals 0, which is less than 1. Yep. And then this should also add then, since the absolute value of a sub n diverges and a sub n converge, it's supposed to be a comma, then a sub n converge conditionally will be your answer. Okay, I'll let you look at that for a second. Okay, okay, what is this? Okay, so this example is like saying that sometimes it's just like easier to do the absolute value of a sub n first to find just a sub n. So I guess in this case here, because there's no like clear alternating like sign, right? Because it's just cosine of n, and it's only alternating when it's cosine pi n, right? So remember that this is not alternating right here. Right, so if we do a sub n first, I mean the absolute value first, we do absolute value and then absolute value of this, right? But since it's n squared, we know that's obviously positive, so we can just ignore the absolute value bars. Okay. So I think in this case we're going to be using the direct comparison test because we can't, like, you look at it, you kind of have a hunch, and you have to decide what test you want to use. So in this case, we're going to use direct comparison test. So let's this is n equal n squared, right? And then using that, we could just use the p-test. So equals converge p-test, p-series, whatever. And then our little explanation p equals 2, which is greater than 1. Okay? So then, using this, we could just write since and converge and so this been then a sub n converge by the direct comparison test, then a sub n converge absolutely. Right, and then we can like just kind of use the assumption that since the absolute value of a sub n converges, then a sub n is also gonna is always gonna converge when we use this, right? So based on that, we can say that that a sub n converge absolutely. Okay, and then now, okay, this is now the third part of like alternating series I was talking about. This is the alternating series estimation theorem. Now I'm gonna be real with you, twin. I'm like 99% sure of what I'm about to teach you. So like, if there is like a little lie, just know that it wasn't on purpose. And I am trying my best. Okay, okay. Okay. So basically, here, I'll write it out. So basically, this theorem is when we have like an alternating series, it's gonna look like this, right? It's gonna look like so whatever thing is, right? So whatever that is, when you like write it all out, it's gonna look like this, right? Okay, I'm gonna try to write a little bit neat so you can actually read this. And like whatever, right? Two, and then whatever. All of this is going to equal the sum, right? Okay. Here, I'm gonna move this actually. This is all going to equal the sum. Okay. Now, we can like just looking at this, you know that like all this is going to be the sum of n, right? S of n. Okay. And then based on that, we can assume that everything else is going to be the error. Okay. Right. Whatever is outside, and then you see whatever this is saying. This is basically saying that that the error is equal to s minus s of 4. Okay, so basically what this is saying is that the sum of the whole thing right here minus s of whatever n is, okay, whatever n is going to equal, well, not equal, it's going to be bounded by this one right here. So it's saying that whatever we're trying to find, or whatever like the estimation thing is, it's going to be bounded by whatever is just outside of n. So like we can see here that b n plus 1 is like the next one, right? So it's whatever is before that is going to be our s of n. So that's what this is saying. Okay, I try to like write it out and explain it to you. It might be a little bit hard to explain. I'm sorry for that, twin. Okay. Okay, so I'll try to explain this one. Like, well, so okay, so we're looking at this series here. Okay, and we're like, what the fuck? Okay. And then, well, I won't go into it because it's not this lecture. But we look at this and we know that this is like convergent, right? Because it's alternating and it's gonna be 1 over n factorial. So basically, the bottom is just so much like it's growing so much faster than the top. Yeah. So we know this converges. Okay. And then if we try to like if we want to think about this partial sum. So let me read the question first. What is the maximum possible error of using the partial sum as a 4 to estimate the sum of the series? Whatever. Okay. Basically, what this partial sum is saying, if you want to write it out, here I'll write it in orange so you can put that together. So it's saying that. Wait, let me write it. It's saying a sub 0 plus a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. All of this is going to equal our partial sum as a 4, right? Okay, so we can see that, and now we can like, and remember that we're starting from a sub 0 because n equals 0, okay? So that's important. If it's like if it's n equals 1, you start from 1, okay? And then we can see from this that we have 5 terms here. We can't really see, whatever, okay, I'll do it like this. We have 5 terms here. So we're looking at 5 terms. Whoa, what am I doing? 5 terms is what this is saying, okay? So now, okay, I'll do it, I can do it 2 ways, okay? So the first way is like you just write it all out. So we know that this top part right here is going to be our sine, so this bottom part right here is our b sub n. So our b sub n, so if we want to like plug in the numbers, we get 1, so 0 factorial, right, minus 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 minus factorial. And this is just going to go on forever, so I'm just going to write it to like here, okay? Right, and it's going forever and ever and ever, okay, into the sunset. So looking at, since this is partial sum as a 4, and we know that it's looking at the first 5 sums, we can see 1, 2, 3, 4, 5. So this, we know that this is going to be our sum of 4, right? Oh, that's really pretty. And then that means that the next term over, this one right here, is going to be the b and plus 1, or whatever is bounding our thing. So we could also we could also rewrite this as like the sum minus s of 4 is going to be bounded by 1, 5 factorial. And then you use your brain a little bit, and I think this is, okay, I could be lying here, I think this is 1 over 120. And then that's like ish. That's an 8 ish. Okay, so twin double checker right there. Okay, I'm too lazy to do that right now. Okay, but like basically that's what it's saying. Just look at like this part right here. Okay, and that's what the question is asking, right? What is the maximum possible error? Error. So yeah, so that would be your answer. And another way to do it, which I guess is, it's kind of like the same thing, but so if you want to rewrite the thing, so we got and then, so yeah, right, and this is our sine, this is our b sub n. So b sub n is going to equal 1 over n factorial, right? And then you could just plug in whatever, because we know it's 5 series, right? So we know that n will equal 5, so we just rewrite it as like this. 5 equals 1 over 5 factorial. Yep. Yep, and that would be your answer. Yep. Hope that makes sense when I try to explain the solubility twin. Another thing they can ask is, like, how many terms are required to approximate the sum of the series, whatever, in order to guarantee that error is less than 0.01. Okay, so in this case, they're telling us what like the bound is. So in this case, the bound is 0.1, and you can also write it as like that. Ooh, that's 100. Let me rewrite that. Okay, perfect. So you can do it like the first way, which is just like writing it all out. So if we plug in, see, n equals 1, so we plug in 1 here, so that's just going to be -1. And then the next one is 1 over 8, because if you plug in 2 instead of n, it's 2 to the third, right? So then you just do that for how many? Well, in this case, we know that the bound is 1 over 100, right? So we're going to keep writing until we get to a number that's less than 1 over 100, right? And that's when we know to stop. So that's when n equals 3, so n equals 4, then n equals 5, and then, okay, so now we can see that 1 over 25 is less than 1 over 100, right? Which is what we're looking for. See, so we know that this is going to be the sum that we're looking at, or so this is, in this case, is sum of 4, because there's 1, 2, 3, 4 terms in it, and then that's going to vary into 4 terms. Because, yep, right, because this is less than 100, so this is our bound, okay? Another way you could do it, it just changes based on like organization, and also like how many, like how big the thing is. Like you could write it like in a chart like this, so b sub n, so in this case b sub n is 1 over n to the third power, right? And then for our third column, and this is like our yes or no, is it less than 0.01 or 1 over 100, okay? So this is what our column will look like, a little bit prettier, I hope, right? And then, so in this case, here, so n equals 1, we plug in 1 here, it's just 1, right? So is this less than 1 hundredths? No. Okay, so we do the next one. This is usually helpful when you have like I guess like bigger things, like if it's a bigger jump. Like in this case, it's not a great example because the 1 over 100 is pretty small, and like when we like when you do like this, you can like jump numbers. So instead of doing like 1 to 2, you could just if you like, you kind of just like guess, right? So you could jump like straight to 4 if you have a feeling, right? And if you do reason 4, it's 1 over 64, and we know, nope, this is wrong. But we can see that 1 over 64 is getting close. So we can just do the next one. Equals, and then this is 1.5, and is this less than 1 over 100? Yes, it is. So this would be where our cutoff is. And then we could use the left side to determine, yep, this is also going to be 4 terms. So yeah, that's just like 2 different ways to do it. I also think that you can use algebra sometimes. I think you can use algebra. It's just going to be like easy or hard depending on the series. So here, I'll try it. I'll write it in red. I don't really recommend using this, but if you want to, whatever the fuck, do algebra, okay? Do whatever your heart wants. So you set it up like, sorry, and right, and that's going to be less than these plus 1, okay? And then, so we know that this is going to be equal to that, so this is going to be equal to plus 1, 2, here's our piece of it, right? See, I switched the sides here, you see, wait, here, I'll write the other side. This side is not on this side, and then this side is not on this side, you see? Okay, so, and then algebra, right, so then you can flip these, plus 1, this is the exponent, sorry, can't read that, right, and then you do cubes of shit, and then, so then it's going to be n plus 1, and then that's going to be equal to 5, and then n equals 4. So I guess you could do it like that. In this case, it's like easy, because like the series is not that difficult, but if it's like more complex, algebra like might not be the best way, but you could, that's an option. And yep, that's the whole lecture, Twin. Good luck, Twin. Let me know if you have any questions, Twin. And yep, good luck, have fun. Okay, bye.